Hey, welcome back to Fat Mama Physics. In this video, we are actually going to be talking about polarization. Polarization of light. So, I'm jumping straight into examples. Hopefully you've covered most of the material either in class, on your own, or maybe having watched a few videos. So, this will be solely doing these examples that I have here, example 1 and example 2, on what we call Molles's law. This is a direct application, or this is quantifying how much light has been polarized. So there's a few things that I'll need you to know. First of all, I need you to know what it means for something to be polarized. A good example would be some of your sunglasses might have polarizers in them. Great for blocking out specific light reflecting off certain surfaces. And the other thing probably is I will actually talk about this one because just in case you missed it, or you're not sure, or if I didn't cover it. First of all is intensity. Intensity is measuring how strong a wave is, but we're kind of used to that already. We use something else to characterize the strength of a wave by looking at what we call the amplitude. The intensity of a wave, and in our case, it's going to be light. We use intensity, which has some relation to amplitude as well. You don't need to know exactly what the relationship is, but the relationship is the following, and this is going to come back again and again and again. First of all, intensity is directly related to the amplitude squared. Okay? It's directly related to the amplitude squared, meaning if you double the amplitude of your wave, you're going to quadruple your intensity. So it's directly proportional to the square of amplitude. The other thing we want to know is the units, which is in watts per meter squared. Okay, so watts per meter squared. If you take a look at the meaning of this, W for watt is a unit of power. Okay, and then meter squared, it's almost representing pretty much what you're thinking of, the area of something. So if you imagine the intensity, if I try to measure the intensity of light, imagine I had an area, a specific area, which is say 1 meter by 1 meter, let's say 1 meter by 1 meter. How much power, how much energy, well, this is not just energy, but the rate of which energy is emitted onto this particular area is going to give me the intensity. In terms of light, the more little packets of waves that hit this particular area per unit of time, the larger your intensity is going to be. So power is not just the amount of energy, it is the rate of which energy is hitting this piece of area, which is going to increase with power. Okay? So the other thing is, how does this relate to Molles's law? First of all, as you were doing either some experiments or some videos, you notice that as you move the polarizers around, depending on the angle between one polarizers versus the other one, that changes the amount of intensity of light that passes through your polarizers. That's what this angle here is trying to tell you. It's the angle between the incident polarized light and the polarizer's transmission axis. So I'll talk about that one in an example in a moment. So one thing is here, this one I is the intensity that is transmitted. The second one is I naught. That 0 means naught, as in kind of like initial if you think about it that way. That is the incident intensity. So how much intensity of light you started off with. You might be wondering why there is a square in the cosine. The square in the cosine has something to do with this amplitude squared factor. So imagine you have some amplitude, you take a component of the amplitude, but then you want to find out the intensity, you have to square the whole thing, and squaring the amplitude is going to give you some factor of intensity, and squaring a cosine theta, which is a component factor, will give you square of cosine. And that's where that square comes from, if you're wondering. The other thing you definitely need to know before this one is the fact that any light going through any polarizer is going to have the intensity of unpolarized light. So if I take, say, if I take a polarizer and put it out into the sun, After I look through my polarizer, I'm going to get exactly half the intensity of which when the sun is shining onto the polarizer. So if I took direct sunlight versus a polarizer, that's exactly half of the intensity going through the polarizer. Okay, so that's another thing we need to know. Okay, so let's start with examples. Example 1. Vertically polarized light, if intensity I0 is incident on a polarizer that has a transmission axis at 30 degrees to the vertical. A. Calculate the factor by which the transmitted intensity is reduced. So we're saying that we have vertically polarized light. So we got this guy over here coming in. So this, we're going to call this I0. And this polarizer is angled. His transmission axis is the axis of which the polarizers allow light to pass through. So if this is making 30 degrees with this vertical, it kind of would be like this. It's kind of off at an angle. So imagine if for your polarizers, all the slits were aligned. The alignment of all those slits would be the transmission axis, and this one makes an angle of 30 degrees. So imagine the vertical is this one. This one here is 30 degrees. So only part of that incident light is going to pass through because a component of it is 30 degrees to that, okay? So if we want to put this one into our Moses law, we want to find out the I, okay, which is the transmitted intensity. This one is going to depend on some factor of I0. And then we're going to use cosine of 30, but this is squared, don't forget that. And notice one thing about cosine of 30. Cosine 30 is actually one of your special triangles. And if you know your special triangles, you probably will know that cosine of 30 is exactly square root of 3 over 2. So if I take the square of the cosine of cosine 30, then that's going to be square root of 3 over 2 squared. And hey, this is exactly, well, 3, square root of 3 squared is just 3. 2 squared is just 4. Hey, that's just 3 over 4, 3/4. So, oh, and there's the I0, which means the factor which the transmission intensity is reduced, it is reduced to 3/4 of my initial intensity. Okay, so that's where you get that one from. So this is the factor here. After you calculate the cosine factors and everything, that gives you the how much is reduced to. Okay, so next one is B. The transmitted light is then incident on the second polarizer, whose axis is at theta equals 60 degrees to the vertical. Calculate the factor by which the initial transmitted intensity is reduced. And this initial which the initial intensity, we have to kind of assume that is from question 1A, which is this guy over here. So this is I0. Okay, so then let's draw everything out again. So the first polarizer was 30 degrees. 30 degrees to the vertical. Okay, now the second one is 60 degrees to the vertical. The second polarizer is 60 degrees. So I'll use orange, I guess. Okay, so this guy is, large tilt there. So relative to this one, it is 60 degrees relative to the vertical. But we have to be very careful because when we try to find the angle, it is always the angle between the incident polarized light and the polarizer's transmission axes. When the light leaves the first polarizer, which is angled at 30 degrees, that means it only makes the angle between that light and the second polarizer is only 30 degrees remaining. After the light leaves the first polarizer, it's going to be only 30 degrees to the second polarizer. So that is what we have to be careful about. Okay? So when we do this question, first of all, we know that the factor going from vertically polarized light to the first, going through the first polarizer, we're going to get our light reduced to 3/4 of our incident. Now, if the light passes through the second polarizer, in which this over here is going to be our new incident for the next equation. This one is going to be this times another cosine squared of not 60, but 30 degrees, because the light leaving the first polarizer will only make a 30-degree angle to the second polarizer. So we take so we have to multiply by this new factor, which we know is cosine square of 30 is 3/4. So essentially what we're doing is we're taking our initial intensity, this guy over here. After going through the first polarizer, we multiplied by 3/4. Going through the second polarizer, we multiply by another 3/4, in which 3 squared is 9, and 4 squared is 16. So the factor which the light is reduced to is 9/16, right there. And that's our answer. Okay, so yeah, it's a little bit tricky to visualize there. Okay, so remember, the angle, what this question is trying to test for is it's trying to make sure that you understand that the angle that you use is always between the light that is actually passing through that polarizer and the transmission axis. Okay. Second question. Unpolarized light is incident on the first polarizer. Okay. And we do know, okay, let's finish the question first. A second polarizer whose transmission axis makes an angle of 25 degrees with the first polarizer. Calculate the fraction of incident light intensity that is transmitted through both polarizers. Now, the question doesn't tell you what transmission axis in this guy, that's the first one, the first polarizer, but it does tell you that whatever this light leaving the first polarizer is going to make a 25-degree angle with the second polarizer. So, because it tells us that angle, we don't have to worry about trying to figure out relative to the vertical, horizontal, whatever. We know that this angle here is going to be 25 degrees because it is relative to the transmission axis. It's the 25 degrees relative to the transmission axis, and that's all we care about. But what this question is kind of getting you to think about is when you have unpolarized light onto this first polarizer, we know that the intensity is halved. Okay, so intensity, let's say this is a I naught, then this is half of I naught after going through the first polarizer. So we have to factor in the half after when we calculate our final answer. But we do know that after going through the second polarizer, this is 1/2 of our initial intensity times the cosine theta of 25 degrees. So if you put into your calculator, what is cosine of 25 degrees, and don't forget to square it, it is, this guy over here is 0.82 ... So then if we take half of that, so divided by 2, we are going to get 0.41, etc. Rounded to 2 significant figures, that is our answer. So our intensity, original intensity of our unpolarized light will get reduced to 0.41 of our initial. Okay, so these are the 3 questions. I think they give us some coverage. Hopefully this will help you with the rest of your questions. Thank you so much for watching. I'll see you next time. Fan Mama Physics signing out.